Okay, welcome everyone to today's seminar, our joint seminar between GQFI at Potsdam and the Warsaw String Theory Group. Today we are very, very happy to have one of our own, Hugo Camargo, who's going to tell us about complexity and entanglement of purification in free CFT tools. So Hugo, please take it away.
Thank you, Ignacio. It's strange to be on the other side of the screen and now being able to share my work with you guys. And I hope you can all hear me well. And I also expect many questions as always. And feel free to interrupt. There may be some delay in the audio. So if I don't answer, it's not that I'm ignoring you. It's maybe just some technical issue, but please go ahead and stop me at any point. And yeah, so today I want to tell you about a recent work on complexity and entanglement of purification in free CFT2s. And this is work that was done in collaboration with these great people, Lucas Hackl, Michal Heller, Alexander Jan, Tadashi Takayanagi, and Bennett Wind. Some of these people are also in the audience, and that's great. But yeah, I encourage everyone to ask about this very interesting paper. And let's go. So as you're all familiar with, in holography, the lore is that the emergence of the space-time is encoded in quantum data at the boundary CFT. And one primal example of this holographic duality is entanglement entropy, which acquires a geometric description in terms of the Bekenstein-Hawking entropy of a codimension 2 extremal surface. So the entanglement entropy associated to a subregion in the boundary, let's call it A, it's going to be given by the area of this minimal surface that is anchored at the boundaries of this time slice. Of course, entanglement is not the only quantity which has been the center of attention in recent times. And it was proposed some years ago that there was another quantity called holographic complexity, which can be obtained through codimension 0 and codimension 1 objects in the bulk. And this quantity is conjectured to encode additional information about states to which entanglement entropy is insensitive. And there's a motto, which is entanglement entropy is not enough, and holographic complexity encapsulates this idea. However, recent developments have also brought a notion of complexity in the realm of quantum field theories. And in this context, there were some great papers in which one writes complexity as in the notion of, in the sense of quantum circuits. And it's in this complexity is interpreted as the difficulty associated with preparing a pure state, let's call it a target state, via some unitary transformation U, starting from some, let's say, typically especially disentangled reference state psi R. And in the Nielsen approach to complexity, which is also the main path that people take when studying complexity in quantum field theories, we usually decompose or rewrite this unitary transformation in terms of more elementary gates via some path order exponential in this way. And the game in complexity is to define a cost function associated to the quantum circuit and then minimize it. And in this way, complexity really captures the difficulty of preparing a state, a target state starting from a pure state. And one special notion of complexity that will be at the center of the talk today is going to be the L2 complexity, which can be written in this very nice way. And the nice interpretation of this measure of complexity is that it's associated with geodesics in this, the space of states. Now, that's great, but so far this discussion in QFTs has been centered on the study of pure states. However, it's also very interesting to ask about the properties of mixed states and what are the gravitational duals in holographic theories. And the two notions that I will tell you about today, which are entanglement and complexity of purification, they arise as natural generalizations of these quantities for pure states to mixed states. Now, when we talk about purification, we obviously talk about embeddings of mixed states in enlarged Hilbert spaces, which in general is a very challenging task. So in order to actually gain to do something practical that will teach us many lessons in physics, we will restrict ourselves to the most general Gaussian purifications of Gaussian mixed states. Examples of these states are, for example, vacuum subregions of free QFTs or CFTs. And the particular setup that we will be looking at is the two-interval vacuum reduced density matrix on a periodic lattice. So in a sense, we will consider field theories, we will discretize field theories, and we will put them on a periodic lattice, and we will study these two notions in the setup where we, for example, have two subsystems that consist of a finite number of lattice sites, and which could be in principle also be separated by a finite number of lattice sites. Now, sure. Was there a question? Okay, I think not. Is the audio okay? Can everybody hear me?
Yep, loud and clear. Well, there is some lag sometimes, but I think it's okay.
Okay. Yeah, just checking in case there was a question. Please stop me at any point. Now, the idea is that, of course, because we're dealing with quantities that are basically new in the context of quantum field theories, we need something as a basis for our understanding of these methods that we will be developing. And mutual information will served us as a guidance to understand, in particular, for example, the behavior of entanglement of purification, and also to understand the subtlety of our discretized models. For example, notions of locality and certain divergences associated with the mass of, for example, the Klein-Gordon field. And in reality, what we want to do, or in practical terms, what we want to do is we want to find the scalings of these three quantities as functions of the size of the subsystem, the separation maybe, the total number of sites, and the mass. And something that we can say from the beginning is, because of the way that entanglement of purification and complexity of purification are defined, which I will do in a few moments, we can say that entanglement of purification is going to be a UV finite quantity, whereas complexity of purification will require some regularization. And we need to consider something that's called mutual complexity, which is something that is akin to mutual information. So I will stop for a few seconds and ask if there are any questions about these very general ideas. Okay, seems like there aren't. So let me tell you about the two models that we studied in our paper. And we wanted to do both bosonic and fermionic CFTs. Now, the basis for these studies were the Klein-Gordon field, and in particular, the discretized version of the Klein-Gordon field. That's one way of handling UV divergences. So this is, as you are familiar with, this is the Hamiltonian of the discretized Klein-Gordon field with some finite mass m. And we can write it in terms of canonical variables in this nice way. Now, the important observation that we have to do in this case is that the ground state of the Klein-Gordon field is Gaussian, and hence it is fully characterized by its covariance matrix. And in this case, the covariance matrix acquires a very nice way in a very nice form in momentum space. And of course, one of the subtleties of the Klein-Gordon model is the zero mode. And I will comment on the zero mode later, but bear in mind that this is a natural, let's call it, feature of discretized models, that we have divergences associated with the zero mode. Now, the second model that we will be considering is the transverse Ising CFT. And although the starting point of this analysis was the Ising model written in terms of spin operators, through a series of steps that involve Jordan-Wigner transform, we bring the Hamiltonian starting from the spin operators to a Hamiltonian that can be written in terms of Majorana operators. And in particular, we choose the part of the Hamiltonian, because we can divide it into a periodic and anti-periodic Hamiltonians. We choose the periodic one and take it as our basis. And the observation in this case is also that the ground state of the critical model, so when these parameters j equals h, is also completely characterized by its covariance matrix. And this is obviously an interesting fact, and a notion that will also be, that I will discuss later, is the notion of locality and what it means in the context of entanglement and complexity, because locality is something that is different from the spin and the fermionic picture. Okay. Now, let me start with mentioning a few things about entanglement of purification. And it's an very interesting notion that is probably not too old. I think in 2004, the first paper came out where they mentioned entanglement of purification. And it's a notion of correlations that brings classical and quantum ones together. And it's a generalization of entanglement entropy. See, because the idea with entanglement entropy is that one starts typically with a pure state, then one chooses a subsystem, then traces over the complement, the degrees of freedom that belong to the complement of this subregion, and computes the von Neumann entropy. But the starting point of entanglement entropy is a pure state. But what happens if we start with a mixed state? Is there a notion of entanglement that we can naturally associate to a mixed state? And that's the idea of entanglement of purification. So the way to think about it in very general terms is the following. So suppose that we have a mixed state, and we can purify it in the following ways. We have, for example, two subregions, A and B, in which the state is mixed, and then we purify it by considering ancilla both for A and B, subject to the constraint that tracing out over this ancilla will recover the original density matrix. And now in this case, entanglement of purification will be defined as the entanglement entropy associated with tracing out one part of this new enlarged Hilbert space, for example, B and B prime. And we do this minimization over all possible purifications that admit these conditions. And that's the idea of entanglement of purification. Now, recalling the setup that we had earlier, we want to study entanglement of purification for both the bosonic model and the fermionic model. There's a close relation between mutual information and entanglement of purification, although there are some subtleties. But the idea is that with entanglement, we can study what happens in the adjacent interval case. So that means when the A and B subsystems are adjacent to each other. And it's very, very interesting to see that one really gets a close agreement with the behavior of both mutual information and the holographic expectation in the context of path integral optimization and entanglement wedge cross-section. So there's a typo here. This one should be fermionic and not bosonic. But nonetheless, it's a really straightforward check to see that this is indeed very close agreement with these in this context. Now, for entanglement, the disjoint interval case. So what happens when we bring these two subsystems apart?
Can I ask a question?
Of course.
Can you go back? In the previous slide, you had these sort of numerics above, and then you have formulas below. How did you get these analytic formulas?
Oh, these analytic formulas. So as I said before, we use the behavior of mutual information sums as some part of a guidance as to what to expect for entanglement of purification, but also there are some holographic expectations on what kind of divergences you would expect to have for this quantity. So what we did was we assumed a very general form of entanglement of purification that more or less had this logarithmic divergence. And then we obtained the data for different number of lattice. And from that, we then recovered the coefficient and the exponent in these two cases. But it's indeed an analysis that is strongly based on the expectation for mutual information and for the holographic entanglement of purification.
Okay, so it's not like you were actually able to find this minimum overall purifications that you showed in the previous slide and you got this thing, but rather you made an educated guess. Okay, now we're back. Go.
Okay, I'm back.
Okay, go ahead.
I forgot to mention is that, can you hear me? So one thing that I forgot to mention in the previous slides is that, of course, in general, the space of the enlarged Hilbert space has, in principle, infinite number of degrees of freedom. So we can purify a mixed state with arbitrary number of ancilla. But there's actually a very nice conjecture that that was made in a parallel paper to this one, that it is actually sufficient in the context of Gaussian mixed states and Gaussian purifications to consider the minimal number of ancilla to purify these states. So the idea is to take these subregions of, in this case, both the fermionic and the bosonic CFT, then consider the most general purifications with the minimal number of ancilla, and then perform the minimization of this functional. And in this case, these points, the blue points in both of these plots correspond to the data gathered from this minimization process. So then, of course, the question of how to actually get let's call them these formulas, it came actually from the data, but also from the guidance of what to expect for mutual information and for entanglement of purification at the level of path integral optimization. Was that more or less clear, Ignacio?
Yeah, thanks.
Okay. Are there any more questions? Okay, then I will continue. Oops. Yeah. So let me come back now to a bit of the discussion regarding one of the subtleties of our models, which is locality in the case of the spin and fermion Ising CFT. In order to actually do the disjoint interval case, one needs to be very careful with this notion of locality, because the spin and the fermion picture, in the spin and the fermion picture, locality is different. And one can see this when one does, for example, the Jordan-Wigner transform. One sees that what in the spin picture, a setup is local. In the fermion picture, that is not the case, because the anti-commutation relations and the trace and the operator, the tensor product in terms of fermionic and spin variables is not equivalent. So because of this, one can also see that for the Ising CFT, considering disjoint intervals basically amounts to considering non-Gaussian setup. So because of this, we focused solely on the bosonic case for disjoint intervals. Now, for example, one can see what happens when the separation between these two subsystems is smaller than the size of the systems, and one finds a very nice and consistency with holographic and path integral approaches. An interesting thing to see is, of course, something that arises in these discretized models is the mass. One obviously, in practical terms, one takes small mass. one cannot set the mass directly to 0. But one can very nicely isolate the mass contribution in these models in this way. And one can focus on the behavior of entanglement of purification, on the divergent, the divergent structure of entanglement of purification in terms of the subsystem separation. And of course, for example, in this case, it's consistent with these formulas. The first one here, this one comes from path integral optimization, and this one is basically the formula for mutual information that one gets from doing the QFT, the CFT analysis. On the other regime, on the other side of the spectrum, we have what happens at very large distances compared to the sizes of the systems. And in this case, we find a subpolynomial decay. That means that we have some decay in terms of this polynomial, and we were not able to actually get the exact exponent in this case, but we were able to have a bound on the exponent of this divergence. And this is similar to what we expect in terms of mutual information, because for mutual information, at large separations of subsystems, one expects that the contribution in the operator expansion comes from basically this term here to an exponent, which is the conformal dimension of the lowest operator. And one sees that in this case, one should expect something that is constant. We get fairly close, but we believe that this is a very good indication that these Gaussian methods are good up to some point, but we don't actually recover the practical expectation. Now, let me move on now to complexity. And if complexity is a measure of the difficulty of preparing pure states, then complexity purification generalizes this notion of preparing mixed states. And the idea is simpler than entanglement of purification, because one considers only a subsystem A in some Hilbert space, and then one enlarges the subsystem to include some ancilla degrees of freedom, in which there exist in principle many purifications, such that once we trace out this ancilla, we recover the original density matrix. And now in this case, as well as with entanglement, we define complexity as the minimum of a pure state complexity measure with respect to some reference state over all possible purifications. Now, this is again important to say, whereas in the case of entanglement of purification, there were some robust studies in the parallel paper that I mentioned, in which it was realized that minimal purifications were sufficient to achieve the minimal Gaussian purifications actually were sufficient to minimize this function. For complexity, the story is a bit more complicated, and there we have some numerical evidence that minimal purifications are sufficient, but we don't have a really robust statement regarding minimal purifications. But for practical terms, we do choose minimal purifications, I mean. Now, it's also interesting to visualize what complexity means, because complexity should measure also in some sort of distance between two states in Hilbert space. So in this context, we have, for example, let's say a target mixed state and some mixed reference state that lives in the subsystem. Now, complexity what does, or the way that we proceed to calculate complexity purification, is we purify both of these states in some way that is allowed by unitary transformations in the symplectic group, which is the group associated with covariance matrices and Gaussian states. And then we have some freedom left over to actually have a target state. And then complexity purification will measure the distance from this purified reference state to this family of target states. And the minimal one will be the state that we choose to have the minimal of complexity of purification. And one interesting thing that we can say, for example, to actually understand a bit of the subtlety between entanglement and complexity is look at the very simple setup of two harmonic oscillators. And for example, in this case, one has a covariance matrix which can be very nicely split into blocks, into a block structure, where one has a block corresponding to, say, one of the oscillators, and then the other block corresponding to the other oscillator, where the off-diagonal part is gives the correlations between these two oscillators. Now, for example, if we were to compute entanglement entropy, then entanglement entropy would only be sensitive to one of the blocks. So in reality, it would be determined by the spectrum of the reduced density matrix associated with one of them. On the other hand, pure state complexity will be something that is sensitive to this full covariance matrix, thus having quote unquote more information than entanglement entropy. And mixed state complexity will be something that fixes this block here and then produces and then minimizes over the rest of the correlations, thus obtaining a measure of complexity of purification. And the setup was studied in this paper here, where some of the authors are also in the audience. And one lesson that we were able to gather from these studies is that complexity seems to satisfy subadditivity, which is something that in the context of holographic complexity proposals was an open question. Let's say, what would be the behavior of complexity at the QFT level? And this subadditivity, for example, is not satisfied by the volume proposal, but it is satisfied by the action and volume 2.0 proposals. So this subadditivity was something that we gathered from this simple setup for two harmonic oscillators, and we will come back to this later. Now, in reality, what did we do in the context of our paper? We considered, as I said at the beginning, the game in complexity is to consider a cost for circuits. And there are in principle many choices that one can make based on different assumptions. The one that we chose was the L2 cost function, which is based on geodesic distance. And this notion of pure state complexity is the one that we minimize starting from a mixed state. Now, in this context, we chose our reference state to be a spatially unentangled subregion, and the target state will be the vacuum subregion. So the idea, as I said, is to minimize this functional over the most general Gaussian minimal purifications. So, for example, for complexity, in the case of the bosonic CFT, we find a divergent structure that looks like this. We first of all find this W over delta leading divergence with a coefficient that is dependent on the reference state scale. We also find subleading divergence that is logarithmic with another coefficient that also depends on this reference state scale, but also the mass of the Klein-Gordon field. And we find some other terms that are not, some constant terms that don't depend on the size of the subsystem and delta. The square root over here can be understood basically by this square root that appears in the L2 cost function. Now, something that's interesting to say is that there is a very big difference between the bosonic case and the fermionic case, because in the bosonic case, when we compute complexity, the reference state, which is spatially unentangled state, comes with the reference scale. This means that this is an extra parameter that arises in the bosonic case naturally. In contrast, when we consider the Ising CFT, if we at the same time want to consider a spatially unentangled subregion, which is also translationally invariant, then basically this state is fixed and is unique. So therefore, for the Ising CFT, there is no reference scale, and the divergent structure is similar, where the difference is that, of course, for the Ising CFT, we don't have parameters such as the mass or the lattice spacing, which is set to 1 in this case. But the divergent structure is the same. Now, as I said at some point, for the adjacent interval case, because we're considering two intervals, we need a notion that we need a regularization of complexity. And in the same way that, for example, entanglement entropy is divergent when considering two intervals, a combination that brings it to, that regularizes it is mutual information. In the same way, one considers something called mutual complexity in this case of purification. And in the particular context of our work, we considered one that was motivated by the use of the L2 norm. That is to say that we consider this particular combination of the complexities of purification associated to each of the subsystems, and then subtract from it the square of the complexity purification to the union of these intervals. Now, in the same way as with entanglement of purification, the data points that you see in these two graphs separated in terms of like fermions and bosons were obtained via this method of the procedure, sorry, of minimization of the complexity functional. And coming back from the analysis of the single interval case, we see that some of the coefficients remain in this two interval case, but the leading divergences, which is the size of the subsystem, basically the volume of the interval, they drop out, and we are left with this logarithmic divergence, which is also reminiscent of what happens in the case of entanglement and mutual information. But now also we have coefficients that depend on these parameters, which are the mass, the reference state scale, and the lattice spacing, which is of course rather interesting, because one can then say, well, we have some very nice expectations about entanglement of purification in terms of the entanglement wedge, but of course we also have some expectation for complexity, not only complexity associated to pure states, so the first complexity proposals in holography, but we also have some expectation to sub-region complexity in holography. And of course, the idea is to see how do these numerical results fare with these expectations coming from holography. And as I said, it's very interesting that this leading divergent structure that we observed for complexity is also present in the holographic subregion proposals, particularly what are called the volume 2.0 and the subregion equals action proposals. So for example, for the single interval case, we also see a similar divergent structure where we have the leading term, which is the size of the system, basically. We also have a logarithmic divergence, and we have some constant terms. Of course, when one studies the action, one has this additional parameter that arises naturally because one considers null boundaries, which is this counter term parameter here. And this L here is the ADS radius. But what's important is that the divergent structure is strikingly similar. In the adjacent interval case for these two proposals, we also find this kind of behavior, which is also in quite remarkable agreement with what I showed you in the previous slide. Now, a few questions naturally come into mind, and let me first make a comment, which is that the divergent structure that I showed you for complexity in these cases. So, for example, this one. A similar divergent structure was also observed for pure state complexity. But that doesn't necessarily mean that we would expect the same thing to happen for complexity of purification. What's surprising is that we do. But anyway, the important thing is that this divergent structure is also present for these holographic proposals. And the role, one question that's always that keeps many of us who work in complexity awake at night is this reference state scale that appears in bosonic theories. What's the interpretation of this in terms of in the holographic proposals? What's the correspondence? And one can try to give two answers. One can say, well, you know, these QFT results for complexity and complexity purification have have this this coefficient appearing in front of the leading divergence, which we can think of as basically some overall normalization of complexity, so we can get rid of that. That's one attitude that one can take. The other one would be, well, maybe there's some relation between the reference state scale and the counterterm parameter here that appears in the action proposal. I would say that the relation between these two quantities has not yet been established, and I would say that this is going to be very interesting to actually understand what's the role of mu in the future. Now, it's also interesting to say that when one talks about complexity, there's always there's other things that one can try to do in complexity. And there are, in fact, two approaches for complexity of mixed states that I would briefly like to tell you about, and which are very interesting. So one has, for example, the so-called mode-by-mode purifications, because what we do in our project was we would consider the minimization of the full enlarged state. So we would produce the minimization over all the parameters in this purification at the same time. So basically, one says we have one problem with NA degrees of freedom, with NA parameters, sorry. Now you can say, well, can't you do the opposite? Can't you split the problem of finding the optimal purification by splitting the problem into NA problems of just one mode? And this is the idea behind mode-by-mode purifications. And there's another approach which one can take for complexity of mixed states, which is just to say, well, I can also define a distance function, a geodesic distance in the space of mixed states. And indeed, there's a function that one can consider in the case of bosons, which is the Fisher-Rao distance. And this is a natural distance function in the manifold of covariance matrices, so basically of Gaussian states. And the natural question is, how does our method compare with these two approaches? And it is interesting to see that there's some qualitative agreement in the behavior that one sees in both cases. So for example, in the case of single mode purifications, one sees that this single mode approximation is quite good for not a very small mass, but it gets worse as the mass decreases, which means maybe in the CFT limit, this would not be a very good approximation. Nonetheless, for certain values of the mass, this is a very good approximation of what we actually do in our paper. Concerning the Fisher-Rao distance, we also see some sort of qualitative agreement, but then again, it's not really cut clear. And again, we see some similar behavior in terms of the mass. So basically the idea is that what we did, which was considering the most general Gaussian purifications, actually is, let's say, it's the optimal way of doing these purifications, but in some cases these approximations are not so bad. So let me now just finish with some summary of some of the things that I told you today, and then we will take some questions. So one of the things that I told you was that in the context of mixed states, one can consider Gaussian states, and ground states of free QFTs are Gaussian. And that means that we can have a full description of the problem in terms of covariance matrices and the symplectic group, which is a very powerful tool. Then again, it's also very interesting that these general Gaussian purifications capture the universal properties of both complexity and entanglement of purification for the single and adjacent interval cases in the CFT limit of the theories that we considered. One thing that's interesting and is that entanglement of purification seems to weight quantum and classical correlations differently from mutual information. although there is some similar qualitative behavior at small separations for disjoint interval cases. Of course, there is the subtlety of the zero mass limit for mutual information and entanglement purification. And obviously the zero mode is what dominates at large D. That's why I didn't show you what happened in this regime. One other thing that we can take home from our analysis is that in this more general case where one considers more degrees of freedom, one sees that complexity purification is also subadditive, which seems to indicate that this is the case in general, at least for Gaussian purifications. Then again, it's also quite interesting that using only Gaussian methods, we find a comparison with the leading divergences in holographic subregion proposals, which is quite interesting, I would say. Now, as I said, also this different notion of locality between spin and fermionic picture leads us to the fact that even for small separations, this Ising CFT states are non-Gaussian. So it would be interesting to see what we can do or what techniques we can develop to actually study these non-Gaussian states in the CFT in the Ising CFT. And going beyond Gaussianity, of course, it would bring us a step closer to probing both of these measures in interacting field theories. And so with that, I would like to thank you, and I'm here for any questions that you may have.
Okay, thank you very much, Hugo. So we have time for questions. Okay, I can start with one. So you were constantly comparing entanglement of purification with mutual information. Mm-hmm. But could you clarify a bit what is the relation between them?
Well, I guess in general, the idea is that mutual information can serve as a guiding principle of how entanglement between subregions behaves, and in being entanglement of purification, a notion of correlations between subregions, it would be natural to make some comparison between them. In fact, some of the results that we have point to the fact that even though these quantities are measures of correlations, they are not exactly the same measure of correlations for when you take a mixed state. But the idea is that mutual information nonetheless serves as a guidance for what we can expect from correlations in regimes, for example, where we have subsystems that are separated by small distance, or where we have them to be very largely separated. But I would say that, yeah.
But is mutual information identical to entanglement of purification in some specific limit? Like adjacent intervals in a global pure state or something like this?
Let me try to go back. I mean, for example, if you would look at the adjacent interval case, if you just look, for example, at the adjacent interval case, mutual information would have twice this behavior. So for bosons and for fermions and bosons, you would have C 1/6 and 1/3. So they're not exactly the same, but the behavior is rather, I mean, this logarithmic behavior is similar.
So I just have a comment. I just have a comment for Ignacio. So I guess, like, if you consider like a globally pure state, and the subregion B is like just a bar, so a complement, then like if you were to calculate EOP, what you would get is like the entanglement entropy between A and A bar. So like this is the limit in which they become the same, right? But like the whole point here is that A and B are two non-adjust or like two subsystems of a bigger system, such that the density matrix describing A union B is not pure.
Okay. So when they are complementary in a pure state, then they are the same.
Then entanglement entropy and EOP are the same quantity.
Okay, good, thanks.
Yeah. No, yeah, sorry, I forgot to say this, that entanglement of purification reduces to the usual entanglement entropy in the case where this rho AB is a pure state.
More questions? Actually, can I ask another question? It's about the ancillas A prime and B prime that you were using when you defined this entanglement of purification. Are there any constraints on what these ancilla Hilbert spaces are, or set on a like?
I mean, the only constraint is that once you trace out this ancilla, you recover the original reduced density matrix. But in principle, these ancilla can have as many degrees of freedom as you want. So the only constraint. Can you hear me?
Yeah. Okay, so in practice, when you do the numerics, what do you choose as A prime and B prime? I mean, do you also minimize over these choices?
Yeah, so the minimization is done over the degrees of freedom that correspond to these ancilla, because this reduced density matrix is fixed by the covariance matrix in the bosonic or the fermionic case. So what you do is this covariance matrix that correspond to this mixed state, you embed it in a larger covariance matrix where you also consider some degrees of freedom that correspond to the ancilla. And then you perform the minimization over this ancilla degrees of freedom.
Right, but that larger covariance matrix, I mean, the rank of that matrix is not bounded, right? You can...
Yeah, exactly. I mean, in principle, it can be infinite, but the point that I was trying to make also was that it was found that minimal purifications, so ancilla containing the same degrees of freedom as your original space, are sufficient to actually achieve the minimal of this entanglement entropy measure here.
But you still okay. But still, in that minimal ancilla spaces, you have like a large choice of pure states.
Exactly. But the idea of actually having this Gaussian states is that you more or less know what form, because you constrain the purifications to be Gaussian. So you know what form the covariance matrix of these purified states have. And that's the power of this method, that because you know that these purified states are also Gaussian, you can actually know over which parameters you do the minimization. What we do in practice is we do a steepest descent method, where we generate, we have the space of the symplectic, the manifold of symplectic transformations, and then we also know what the Lie algebra is for the dimension in which we choose for the size that we choose, and then we perform the steepest descent method by generating the Lie algebra elements that lead at each point and leading us to the minimum of this function.
Okay, yeah. Okay, thanks.
Yep.
Hi. Can you hear me?
Yeah.
Good. I'm Antonia. I'm a postdoc in Barcelona, at Barcelona University. Hi, nice talk. I just wanted to ask you, in the end, you say that you use the mutual information as a guidance.
Yes.
For complexity. But so in the end, the result is the same. I mean, do you get the same kind of behavior for complexity, for the mutual complexity in the mixed states, or?
So sorry, you're talking now about the
in general.
This part in general.
Yeah, what I mean,
So
I mean,
what
apart
do you mean?
from
Sorry,
the guide, from the guidance, you say that you use mutual information as a guidance for the behavior of that you expect, yes, for mutual complexity.
I see. I see.
Then,
I think I understand. I mean, what I meant to say when I said that we use it as a guidance, I mean as a guidance to regularize complexity, because as entanglement entropy is divergent, complexity by itself is also divergent. So when we consider two intervals, we also need to find a way to get rid of some divergences that come with complexity. And what I meant to say is that this combination here, so equation 20, is a way in which we can regularize complexity in such a way that we get rid of these additional divergences. So in a sense, we're not taking the actual mutual information in this particular cases as guidance, but rather the idea of regularizing the single interval complexities in this way. Yeah.
so the definition of the mutual complexity.
Exactly. So yeah, so what I meant was basically the definition of this mutual complexity, which, for example, is different from what we would do in the holographic setup, because in the holographic setup, we don't take, for example, the squares of the single interval complexities. We just take the sum of the individual ones and subtract the union in this case. But as I said, for complexity, the squares here are motivated by the distance function that we use, which is the L2 norm. If one would have, for example, an L1 norm, then one would not need in principle to take the squares, but one would still need to regulate.
Okay, thank you.
Sure.
More questions? Well, if not, I'm clapping for everyone. We thank Hugo again.
Thank you.